In today's video, we will see what would happen if two black holes collided. In addition, we will also see the effects of a black hole collision that occurs close to our solar system, and much more. So without further ado, let's get to the video. Black holes are described as monsters because of their exceptionally powerful gravity. Gravity is the force that governs the attraction between objects with mass, and in black holes, this force is so intense that nothing, not even light, can escape it. This creates an extreme and monstrous environment in terms of gravitational force. The description as gravitational monsters also relates to the ability of black holes to warp the space-time around them. This deformation is a direct consequence of the large amount of mass concentrated in a relatively small space. The idea that they can alter the very structure of space emphasizes their formidable influence on the fabric of the universe and may also relate to the invisible aspect of black holes. They do not emit light, nor are they directly observable. The detection of black holes is often based on the gravitational effects they exert on objects around them. If something, like a star, comes too close to a black hole, it can be captured and consumed. Really, they are monsters. But if two black holes collided? Well, initially, the two black holes would move closer to each other due to mutual gravitational attraction. This phase can take millions or billions of years, depending on the masses and distances involved. As the black holes get closer, they would begin to orbit each other in a cosmic dance. This stage is known as inspirational, and during this orbit, black holes would release a significant amount of energy in the form of gravitational waves. Eventually, the black holes would merge into a single, larger black hole. During this process, there would be an event called coalescent dip, marking the final phase of the collision. Merging black holes would result in an extremely powerful release of energy in the form of gravitational waves. These waves carry information about the mass, rotation, and other parameters of the black holes involved. After the collision, the newly formed black holes would go through a period of wobbling as they adjust to their new configuration. Eventually, they would stabilize into a single, more massive black hole. During the merger, the black hole's collision would have the effect of significantly distorting nearby space-time. This would create gravitational waves that would propagate through the cosmos, affecting the very fabric of the universe. Contrary to expectations of a spectacular explosion, black hole mergers are generally not accompanied by a significant release of visible light. These events are mainly characterized by the emission of gravitational waves. Telescopes and observatories on Earth, such as LIGO and Virgo, were designed to detect gravitational waves. Detecting these waves is the main way scientists can infer the occurrence of black hole collisions. According to the theory of general relativity, the presence of mass and energy in space-time causes that space-time to bend around them. Black holes, due to their large mass concentrated in a very small point, create extremely intense curvatures. When two black holes collide, the energy generated during the merger process is released in the form of gravitational waves. These waves carry information about changes in mass distribution and motion during the collision. Gravitational waves propagate through space-time, carrying with them the changes in the geometry of space resulting from the merger of black holes. This is often compared to throwing a stone into a lake, where ripples move across the water. As gravitational waves propagate, they cause very small variations in the distance between objects in space-time. These variations are extremely subtle, on the order of the size of an atom. Dedicated observatories, such as LIGO, Laser Interferometer Gravitational Wave Observatory, have been designed to detect these tiny fluctuations in distance caused by gravitational waves. When these observatories record characteristic patterns, scientists can infer the occurrence of events such as black hole mergers. The successful detection of gravitational waves from black hole mergers represents direct experimental confirmation of Einstein's theory of general relativity. These events provide valuable insights into the nature of space-time under extreme conditions. Astronomers can observe space using a variety of instruments, including optical telescopes, space telescopes, and electromagnetic wave detectors. Black hole detection is often based on observing patterns of light emitted by nearby objects. If two black holes are about to collide, there may be variations in the light emissions from objects around them. This could include changes in radiation patterns from neighboring stars, gas, and dust being pulled into the black holes. As mentioned earlier, the imminent collision of two black holes would result in the emission of gravitational waves. These waves are not detectable by optical telescopes, but rather by gravitational wave observatories, such as LIGO and Virgo. Early detection of these events would allow astronomers to prepare observatories and telescopes to study black hole collisions in real time. This would provide a unique opportunity to observe the final stages of this rare cosmic phenomenon. The discovery and observation of colliding black holes would not only confirm theories about the formation and merger of black holes, but would also provide valuable information about extreme conditions in the universe, contributing to the overall advancement in our understanding of astrophysics and gravity. Two black holes begin to approach each other due to the influence of their mutual gravitational attraction. This initial phase, known as inspirational, is marked by the spiral movement of black holes towards each other. As black holes get closer, they begin to share a stronger gravitational field. This leads to mutual acceleration as the gravity between them increases. During inspiration, the black holes enter an orbit around each other. This initial orbit may be wide, but as the gravitational pull continues to act, the orbit gradually narrows. As black holes orbit each other, they emit gravitational waves, a form of radiation that carries energy and momentum, pulling it away from the binary system. This loss of energy causes the black holes to come even closer together. As black holes continue to release energy in the form of gravitational waves, their orbit decreases in size. This is known as adiabatic inspiration. As black holes get closer, they create a vortex of material around them, made up of gas, dust, and other substances that have been attracted by strong gravity. This vortex can emit detectable radiation. During the final phase of inspiration, an accretion disk can form around black holes. This is a flat disk of material that is being pulled by the black holes, heating up and emitting radiation before being swallowed. Eventually, black holes get close enough that they can no longer orbit on a stable trajectory. At that point, they enter the coalescence, or merger phase, when tidal forces tear apart the space-time between them, and the black holes merge into a single black hole. Fusion results in an incredibly violent release of energy, mainly in the form of gravitational waves. These waves propagate through space-time and can be detected by gravitational wave observatories on Earth. After the merger, a single, more massive black hole is formed. This new black hole may have different properties, such as faster rotation, depending on the characteristics of the original black holes. The presence of black holes nearby would significantly affect the local gravitational field. Planets, asteroids, and other celestial bodies would feel gravitational influences, changing their orbits and trajectories. Merging black holes would cause massive distortions in nearby space-time. This could result in phenomena such as the stretching and compression of space, affecting the local geometry and trajectories of celestial objects. During fusion, the release of energy would be colossal. The radiation emitted by merging black holes, along with any surrounding material that is heated in the process, could have significant effects on nearby celestial bodies. Colliding black holes would generate extreme gravitational tidal forces. This could lead to distortion and even rupture of more fragile celestial bodies, such as comets or planet moons. Gravitational disruption resulting from colliding black holes could alter the orbits of planets in our solar system. This would have long-term effects on the stability of the planetary system. Black hole mergers involve the release of enormous amounts of energy and material. Some of this material can be expelled at high speeds, potentially colliding with planets, moons, or other objects in the solar system. The disrupted environment caused by the collision could affect ongoing or planned space missions. Orbits may need to be adjusted, and space navigation could become more challenging. Merging black holes would generate significant gravitational waves that would propagate through space. Although these waves are extremely weak, as they move away from the source, they could still be detected by sensitive observatories, providing valuable information. Although black hole collisions are extreme cosmic events, it is important to note that the solar system is vast, and on astronomical scales, distances are enormous. This means that a direct impact on life on Earth from a nearby collision would be unlikely. While black hole collisions are impressive cosmic phenomena and fundamental to understanding fundamental physics, the likelihood that they pose a direct threat to our solar system is extremely low, given the vastness and dispersion of interstellar space. So if you like the content, please smash that like button and subscribe so you don't miss the next videos. Bye!